Alright, here's my H-bridge motor control. This is just a quick view of its operations, and then we will go into how to program it, of course. Push one switch, the appropriate LED for one polarity comes on, motor runs in reverse. Press the other switch, other LED, other polarity, motor reverses direction. This is the current limiting circuit. Even if I was to stall out the motor or wire the H-bridge wrong or short it out, that's how you keep from blowing up your circuits until you get it wired right. Alright, let's go look at the programming. And a real quick look at the hardware schematics. The main idea of this video, of course, is to further explain how to properly program and operate a solid-state H-bridge, and to emphasize proper programming. Let me say outright, do not try to switch this stuff on and off with mechanical switches. Don't do it. You need a microcontroller. You need one that operates properly, and you need one that's programmed properly. And there's a proper way of programming and switching versus simply a wrong way. First of all, in this demo, we're using an Arduino. We're using digital pin 2 and 3. We just simply have push button switches wired to ground. We're using the internal pull-ups. So you press one switch, it should go forward, the other switch should reverse polarity. Now let's walk through this step by step. Digital pin 8 through a driver transistor, which is an NPN power transistor. You could have used a smaller one. A TIP41 is what I happen to have and what you saw in the video. Through a 1K resistor, and it's connected to the base of Q1. Alright, this is an argument I've had out of a number of people, and I'm telling you right now, you've got to have this transistor. Do not try to connect this through this resistor directly to your Arduino, or you're going to destroy it. There's 12 volts on this collector. You cannot connect it directly to Arduino. You have to use this transistor, whose base has a 1K current limiting resistor. A high on digital pin 8 turns on the TIP41. It creates a current flow through the base emitter junction and applies whatever VCC is at point A. Digital pin 9 connects directly to the base of Q2. There's not a problem here. If it's high, Q2 turns on, and you have a connection from A to ground. Never, ever turn on digital pin 8 and digital pin 9 at the same time, or you will have shoot-through. This is why fumbling around with switches and bad code will blow up your project. And you'll short the transistors out, you'll blow the power supplies, whatever. Let's continue. Digital pin 11 is used through this TIP41 and Q3 in the exact same manner as Q1 was used. A high will turn on the TIP41, creating a current flow from emitter base, and thus applying VCC here at point B. And of course, digital pin 11, 5 volts, goes directly into the base of Q4, switches it on. Never, ever turn on digital pin 11 and 10 at the same time, because it will create shoot-through, blow your transistors, blow your power supply, whatever. So what we want to do, keep in mind how these are connected, and wire this and connect this exactly as you see it. If you want to go altering the design and thinking you're going to cut some corners or whatever, I'm not going to help you through it. Follow the instructions unless you are. And this is designed for people just getting into this. Believe me, from experience, follow the instructions. Do some research. Understand what the parts are you're dealing with. Like, for instance, if you pull the spec sheets on these TIP 124s and TIP 120s, you'll find out that the suppressor diodes are built inside the transistor. Thus, you don't need external diodes. That's why I like these transistors. I took this design and unplugged all 4 of these transistors and plugged in TIP 41s for Q2 and Q3 and MJE 2055s for Q1 and Q3. Circuit works identical, except if you're going to use regular bipolar transistors. Those did not have diodes, and you'll have to wire in 4 external diodes. All right, over here, to go in, let's say, forward direction, I have to switch on Q1 and Q4. So to do Q1, I'm going to have to make digital pin 8 high and digital pin 11 high, but digital pin 9 and 10 must be off, and they must stay off. To reverse direction, I have to turn on Q2, a high on digital pin 9, and Q3, a high on digital pin 10. At no time during when I switch these two on are you to have a high on digital pin 11 or 8. If you're reversing polarity, turn everything off. Give the motor or whatever a little time to settle. You might want to pop it with a real brief pulse in the other direction, maybe to break it. But most of the time you don't have to do that. So the sequence is, again, if you want to go forward, you turn the whole system off, then you go in reverse. Every time you want to change direction, turn all 4 transistors off. Here are 2 parts to this H-bridge project that are indispensable, and I highly urge you to use them. Use a current limited power supply. That way, if you wire up something wrong, the programming is wrong, and you switch on the wrong pairs of transistors or whatever, you won't blow up the power supply, you won't knock out your transistors, and that goes for MOSFETs or bipolar transistors, whatever you're using. I used a current limited LM317 with a 2.7 ohm resistor. This will give me a max current output of 460 milliamps. As you saw in the video, I actually had a 12 volt light bulb, since it's a 12 volt system in this case, wired from the in to the out. That gave me a visual indicator. If the circuit is shorted, the LM317 will maintain the current at around 460 mils, but the voltage will be dropped across the regulator. The light bulb lighting up across the regulator tells me, hey, it's dropping a lot of voltage. I have a problem. Something's not working here. In addition, before you hook up a motor, when you're going through the programming and wiring and everything, and I can tell you this is happening with people because I've done it in the past. I'm guilty. Okay, you wire it up, you put your motor on, you hit the power supply, and boom, there goes your transistors. Your power supply just blew a fuse, blah blah. That's the story. Before you hook up a motor, connect this instead. Leave the motor off until you know you got the wiring correct, until you have the programming correct. Just put a couple of back-to-back LEDs through a 1K resistor across AB here. When it's working right, you should switch on one LED cleanly, and it should switch off, and then the other LED should switch in cleanly. This way you can make sure that you're not having a miswired circuit trying to drive a motor dragging a lot of current through the system. So these two safety features, do what you want. I would highly advise you to use a current limited power supply and use this before you hook a motor on, and make sure that it's swapping polarity like it should. Now this is where life gets interesting, and for many of you new to microcontrollers, you might as well start learning what's under the hood and how to really program these things. Let's look here on the right. This is an ATmega 168. I use that as an example. It has what is called ports. Usually they're 8-bit ports. Port C ends up being your analog inputs, and it's also one of them's also your reset. Port D is digital pins. Port D is digital pins 2 through 7, and port B is digital pins 8 through 13. Now, I know this looks a little odd. We're interested in port B because you remember that I hooked up my connections to the transistors through digital pin 8, 9, 10, and 11, which is port B0, port B1, port B2, port B3. I have nothing connected to digital pin 12, which is port B4, and I use the LED that happens to be on my Arduino Nano as coming on for only one direction, whichever one, forward or reverse, you want to use it for. Now, as usual, when we want to program a pin for input or output, we're going to use pin mode, whatever the pin is, input. In this case, 2 and 3 are programmed as inputs because I just have switches connected to ground, and I have to do digital writes. You do a digital write to an input in Arduino, you cut on pull-up resistors. That saves you from having to do external resistors. But now I'm going to come to something different. I have 5 pins that I'm using on port B, which is digital pins 8, 9, 10, 11, and 13. I would have to have 5 more pin mode statements and 5 more digital write statements just to program a couple of pins, to turn them on, make them inputs or outputs, and turn them off so the only thing coming out is 0. I'm using what is called direct port access. Your Arduino compiler will do this. Let's look at what we got. Every port, B, C, and D, have corresponding data direction registers. If there is a 1 in a corresponding bit, it's an output. If it's a 0 in a corresponding bit, it's an input. So data direction register B, I want to set for, and this bit right here, which is PB0, is digital pin 8, digital pin 9, digital pin 10, digital pin 11. I'm not using 12, so I left it as an input. And there's digital pin 13, which happens to be PB5. You can't do anything with 6 and 7 because if you look over here, that's where your crystal attaches, your timing crystal or resonator. In one fall swoop and 4 bytes, I can program every pin in that port instantaneously with 4 bytes of code. That's it. And I used a bitwise OR to turn on every bit or corresponding digital pin. If it's a 1, it's an output. If it's a 0, it's an input. So in one fall swoop, I made digital pins 8, 9, 10, 11, and 13 outputs. Boom, just like that. Next, we're going to go to what is called port B. It's really port B data, but it's called port B. In this case, I did a bitwise AND with 0. If I take the corresponding bit, if I broke this out in binary instead of hex, all I did was turn off every pin. Every pin coming out of it that's connected to that H bridge is 0. It's turned off, it's switched to ground. That's what you want. Otherwise, I would have had to resort to 5 digital writes, do each one at a frigging time, which creates timing and other problems when you're trying to actually switch the thing, which is why I went to this. So we're going to use port commands. I'm going to be writing a value to port B that will turn on the appropriate transistors in the H bridge. Alright, this is the entire motor control program that's in loop. We got 2 if statements. I'm checking to see if the switch on digital pin 2 is pressed or the switch on digital pin 3 is pressed. If I press the switch, digital read returns a 0, which when you use the not function will make it a high, and that means the if statement will execute. Let's do this again. That's a not function. The exclamation point is a not function. Whatever digital read pin 2 returns, it's going to be inverted to the opposite state. The if statement will only work if digital pin 2 goes low. So I press the switch, it goes to ground, it goes to 0, 0 not it is a high, and if interprets that as yes, let's do this. What does our if statement do if I press the switch on digital pin 2? First, it's going to do like we did back in setup. It's going to turn all the pins off on port B. I want everything shut off. I don't want to try to write new values to the port with pins still on. I'm going to delay, in this example, 500 milliseconds. Does 2 things. It allows me to get my finger off the switch, but it also allows everything to turn off, the motor to stop, to settle down, and so forth. Then it writes a new value to port B. In this case, remember this bit corresponds to digital pin 8. Digital pin 9 and 10 are turned off. Digital pin 11 is turned on, and so is digital pin 13. Lights up the LED on the little Arduino Nano that I'm using in this example. And that's all it does. Now my motor should be on and running in one direction. Until, of course, I press the other switch. If I press the switch on digital read 3, same deal. It goes low, which is not inverted to a high. The if statement will execute. Again, I want the port turned off. Everything is turned off. I'm going to delay again, gives me time to get my finger off the switch, for the motor to settle down and all the capacitors or whatever's in the circuit to discharge and settle down. Now I'm going to turn on port B with my new values. In this case, digital pin 8 is turned off. I've turned on 9 and 10. Digital pin 11 is off, and digital pin 13 is also turned off, so the LED on the Nano should have turned off. And it will remain in that state until I press this switch again, which will turn everything off and reverse my polarity. And you see right here, I'm writing all the bits in one pop. I'm not using 5 digital writes every time to turn. I'm not using this right here. These 2 statements save the use of 10 digital write. Boy, that makes it a lot easier, doesn't it? You might want to take your digital pins, digital pins 8 through 13. You might want to connect yourself some LEDs to ground through these pins and play with these port values. See and learn how when you have these things programmed as outputs, what bit combinations show up on your LEDs. Now, if it's already going in one direction and I hit the switch again, what it does, it turns it off and then it starts again, because it's going to turn everything off. It's going to wait a half a second, then it's going to write the new value, and off it goes again. This is just a demonstration. Use the code and what I've given you. Use it to try to sit down and understand what you're doing here. Experiment with it. Get to know the system before you sit here and throw some complex item together. Alright, I hope this was useful and gives you a better idea how to handle these H-bridge circuits. Do it safely. Carefully draw out the circuit design that you're using and follow it, particularly if it's mine. Every part in this circuit has a reason. If you take it out, it probably won't work. Use these little safety ideas. A current limited power supply, or this little LM317 current limiting circuit. And before you hook up a motor, make sure you can forward and reverse the voltage polarity. Then sit down. If this is before you even hook it up, you might, like I said, you might want to hook just a bunch of LEDs to ground and experiment with these port values, and understand how this works, because you can use this in a lot of electronics. It's too much of a headache and it creates too many problems to use digital writes to turn off all these pins. It probably will work, but it's not efficient code, and sometimes it creates problems. When I want something switched on, when I want digital pin 8 and 11, I want them switched on now. I don't want to wait. Alright, I switched this one on, then I'm going to bumble around with another digital write, turn that one off. Another digital write, turn that one off. Another digital write, turn that one on. You get the idea? Experiment with this stuff and have some fun. Take your time. And be safe. Thanks for listening. Visit my website at www.bristolwatch.com. Oh yes, a few final words on this. If you want to turn the whole system completely off, where it's not running one way or the other, hit the reset switch. And one other issue you should know of before we leave this video. Arduino, or people who are normally writing C code, who tend to be programmers and not hardware people, will tell you not to use these port commands because there's a problem with portability. If you're using any, and I've tried this on a number of Arduino compilers, you have to sit here and look at what ports you actually have on the Arduino that you're using. It's certainly going to have a port B. They complain it might not be portable from one platform to another. Again, I don't really care about that. I want my circuit to work, and if you understand what you're doing by experimentation, and like I said, maybe you want to hook some LEDs to this and play with these port commands. I have other separate videos that explain these port commands. Watch those, experiment with it, but be aware that this program here might not work on an Arduino that I can't see it happening, but as far as I know, all Arduinos have a port B and digital pins 8 through 13. So, have fun. Thanks for listening.